Hi, my name is Isabella, and today I'm going to be talking about the Piezo1 protein and the mutation that we see at the arginine 2456 and how it is replaced by histidine. So here I have it spanning across the plasma membrane, so we can kind of see how this protein channel is located within, but I'm going to be focusing on using the 3D protein model today. So Piezo1 is a mechanico-sensitive ion channel found within the plasma membrane of cells, and specifically we're going to talk about the mutation where arginine is replaced by histidine. And so this is actually located within the intracellular domain. And so when we're looking at this, we know that this protein is located in many different cells, including endothelial cells, cardiomyocytes, erythrocytes, so it's in lungs, skin, bladder, kidneys, all over really. And so this R2456H mutation is a gain-of-function mutation, and it can lead to dehydrated stomatocytosis. And so we know that Piezo1 normally controls calcium influx to regulate red blood cell hydration, but the mutation keeps the ion channel open for abnormally long. And it results in dehydrated and rigid red blood cells, causing hemolytic anemia, jaundice, and risk of iron overload and gallstones. But we're going to get more into those details. So the normal protein function, so Piezo1, like I said, is a large mechanical-sensitive ion channel, and it responds to mechanical forces like pressure or stretching in cell membranes. So it plays a crucial role in regulating ion influx, mainly calcium, sodium, and potassium levels, and all of these different cations to regulate osmotic balance. So this ion channel, actually we see a mutation because of this arginine to histidine mutation. So we see that this ion channel actually stays open for longer and leads to excessive ion influx, which causes more water loss and makes red blood cells more rigid and dehydrated. So here we have this channel, and so it's staying open for longer and leading to more influx. And so if this represents calcium ions, for example, like normally we have this regular amount, we're doing this opening and closing action of our protein, but then when we have our mutation, we have this influx, and this leads to a lot of imbalances. And so based on the literature, this mutation disrupts the IH pore and the IH pore lipid interaction because we are within this plasma membrane, right? So I'm going to talk a little bit about specifically the amino acids that are being impacted, right? So we have arginine, and so arginine is here at position 2456, and arginine has a pK of 12, so it's positively charged, large polar side chain, so it hydrogen bonds, ionic bonds, because we have a lot of these nitrogens, so that's very good for our hydrogen bonding. We have this positive charge at physiological pH, not displayed here, but that leads to ionic bonds, cations, and always pretty much inner van der Waals forces. But then instead we have histidine, where we have a pK of only about 6. And while it's still basic, we still have, it's only charged in acidic environments. And we have hydrogen bonds and ionic bonds, but there is, as you can see, a major difference in the size and rigidity of our molecules here. So these would include the primary structure and the bonding that's available, okay? And so we have this replacement within our protein. And so our primary structure always leads to secondary structure where we have these alpha helices, right? And so we have alpha helices all spanning within our molecule, or within our protein. But then these alpha helices join with other alpha helices and other alpha helices like this to form our tertiary structure. So this would be part of our tertiary structure, this and this, but all together making that quaternary structure. And so ultimately we have the cellular impact where we have increased calcium influx, destruction of red blood cells, membrane rigidity, but this leads to organism level differences causing hemolytic anemia, increased risk of blood clotting, fatigue, jaundice. And so we have all of these things that we can kind of see within this model. However, we do have some limitations. This is only a simplified model. We can't really see this opening and closing structure of our channel too well, as best as we could. We also have some differences in how we can really display this primary structure. How does the protein folding really lead to this is not well described here. And lastly, we would be able to see the interactions, as I said earlier, with the IH pore molecules if we could see this fully within a plasma membrane. So thank you for listening, and I hope you've learned a thing or two.